The last speaker of this afternoon is David Mond from Norway. We'll talk about the intersection of forms and rest in the real world. So please start.
Okay. Thank you. Ooh. Well, it's a very great honor to be here, a great pleasure. It's a beautiful city. Got some wonderful mathematicians congregated here. I'm very proud to be talking to you all. This talk is joint work. It's based on the thesis of Paul Cadman, who was a graduate student in Warwick and who decided that he didn't want to face the cutthroat competition of academic life, so he's now doing software. And the other contributor is Luca van Straten, who knows a lot about the delta constant stratum, which is what this talk is really about. Am I talking at the right volume? Yes. Thank you. Okay, so we begin with a very basic setup. We take an irreducible plane curve singularity, defined by f, function f, and a right miniversal deformation of the function. So not a miniversal deformation of the curve, but of the function itself. So it has new parameters that equal to the Miller number of the curve. For each parameter, u, we take the fiber, f sub u inverse of 0, that's the fiber of the big vibration here. And d in the base space is the discriminant, which is the set of parameter values for which the fiber over 0 is single. Now, I want to remind you some very elementary things. The delta invariant of a curve singularity is simply the dimension of the quotient of the normalization. So we take the normalization of the curve, which may have several points, maybe a multi-germ, divide it by the ring of functions on the curve itself, and that's take the dimension, that's the delta invariant, and it has a very clear geometric significance. It's the number of nodes in a stable perturbation of the parametrization. So here we start off with a reducible curve singularity. We deform it so that all singularities are simply crossings. We can do this with a parametrization, and we get 3 nodes. So one can check delta defined in this way is 3. So let me continue with a long list of definitions. For each of the plane curves of the fibers, we add together the delta invariants of their singular points and call that delta of the curve. And then we define dk, which is a stratum in the base of the deformation. That's the set of points, the parameter values where the delta invariant, the total delta invariant of the fiber is at least k. So, for example, d itself is d1, because there must be at least one singular point, and any singular point of the curve has got delta at least 1. And d of delta, where delta is the delta invariant of the original curve, is what's known as the delta constant strata. So this is a famous object in singularity theory. There's a formula of Milner that, in the case of an irreducible curve singularity, tells you that the Milner number is twice delta, and in fact, one easily shows that the stratum dk has codimension k, so d delta has codimension delta, which is half mu, so it's a half-dimensional, it's a middle-dimensional stratum in the base space, which is even dimensional in the case of an irreducible plane curve singularity. So these are what are called the Severi Strata. And actually, I slightly regret this. I know that some people call these the Severi Strata, but I don't know why. So maybe I shouldn't call them that. Anyway, here's a picture. Actually, I just downloaded this picture from the internet, and it's, as you can see, it's not a very accurate picture. I mean, the object is all right, but the labels seem to be completely wrong. So ignore the labels. you can see the familiar swallowtail surface, and it's got two singular curves, one here, which is mirrored on the other side, but you can't see it, and then another singular curve down here, where the surface passes through itself. And in this case, this curve is the delta constant stratum, and along here, delta is just equal to 1. And you can easily see that because these points are points where the fiber has a single singularity of type A2. So this is, of course, the discriminant of A3. And along here, the fiber has two singular points of type A1. So for each of these, delta is indeed 1. So delta is 2, as I said. Let's see, what else have we got? Here's a rather lousy picture of an A2 singularity formed out of two latex symbols. So this is, you might see two plane curves meeting tangentially, and then they're perturbed by writing h skip minus 0.1 inch. And this is the perturbation of the parameters. Anyway, so here's there's a picture. Delta is 2, and you've seen the delta constant strata. Of course, this is not an example of what I'm talking about, really, because this is a singularity in dimension with a three-dimensional base space, and that's not an irreducible data. The question that we wanted to answer in Mond's thesis was how to find equations for delta constant stratum in particular. And there's a long-standing conjecture I guess by Duco, by stratum, that delta constant stratum is always Cohen-Macaulay. And we wanted to find out whether we could gain some access towards this. For the singularities A2K, it was proved a long time ago by Eventhal that the delta constant stratum is Cohen-Macaulay. It's the famous open swallowtail. But for the other, even the other simple singularities, E6 and E8, it was not known whether or not this is Cohen-Macaulay. And one reason is because it's rather hard to find equations. So, here's how we proceeded. So, I, for some reason, remind you that the curve is irreducible, delta is half of mu, and I want to remind you about the intersection form. So, there's a intersection form is defined most simply on homology, but there's a dual intersection form on the cohomology. So, to understand it in homology is much clearer. If you have an irreducible plane curve singularity, then the Milnor fiber has got a single boundary component. And that means that for every homology class, there is another homology class meeting it with non-trivial intersection number. This is no longer true if there's more than one boundary component. If you have a curve with more than one boundary component, then the cycle which simply goes around one of the holes is a homology class which is not a boundary, because to be a boundary you have to take both ends. So, in the case of an irreducible plane curve singularity, the intersection form, on the homology and on the cohomology gives you a non-degenerate pair.
The product in the right is the same as the bracket? Or
I'm sorry?
The product in the right is the same as the bracket? Or?
Yeah, oh, you're right. Sorry, this is a typographical error. This here should say pair. That's what I mean. Okay. So, to continue, the cohomology can be all glued together to form a vector bundle of rank mu over the complement of the discriminant. And in fact, one also gets a vector bundle of lower rank over the strata of constant singularity type, the right equivalent strata, which I should mention the same things as integral manifolds of the distribution of logarithmic derivations, der minus of p. And if we take a one form on the total space of the deformation, then this determines a section of the bundle, which we call P sub omega. Simply, to the one form omega, we first of all associate it, we restrict it to the curve C sub u, the fiber. That is one form on a complex one manifold, so it's closed, and therefore defines a cohomology class. So it's a very simple procedure. This is called period mapping. And this was studied by Giventhal and by Varchenko. They introduced the following term. The period mapping is non-degenerate on a stratum if the covariant derivative with respect to the canonical Gauss-Manning connection on the bundle over the stratum is an isomorphism. So I don't want to be too technical. I'd rather not have to say covariant derivative. Just think of the derivative. Just think of trivializing the vector bundle and projecting the ordinary derivative into the fiber and getting a derivative, therefore, from the tangent space to the base into the tangent space, into the, where have we got to? Here. Into the homology of the fiber. And what the connection does is give you a canonical way of making that projection. So you get a canonical derivative, and if this is an isomorphism, then we say the form is, the period mapping is non-degenerate on the stratum. And that's essentially the case kind of generically. In fact, one can be a bit more precise. If F, in particular, what I'm most interested in is the case of the simple singularities. If F is weighted homogeneous, then all that is needed in order that the period mapping be non-degenerate on all the strata is that d omega should be a relative volume form. So Varchenko wrote a paper in which he conjectured this in 1989 and proved it in some special cases. And we recently corresponded with Klaus Hertling, who says that he can show it in general. So in any case, we use omega equal to y dx, very simple form whose exterior derivative is a volume form, on the total space of the deformation, on the fibers of the total space, the ambient fibers of the deformation. And we call a period mapping with these properties simply non-degenerate. So, the interesting thing is that because the intersection form on the fiber is non-degenerate, it's a skew-symmetric non-degenerate form. I hate this controller. It's very difficult to find the right voice. Anyway, because the intersection form, which I'm writing with these angular brackets, is a non-degenerate skew-symmetric form. And because of the way that we define the period mapping, one can prove that the pullback is actually closed, so that means it's a symplectic form on C mu minus D. And Varchenko and Giventhal showed that if d omega is non-degenerate, then this extends to a symplectic form on the whole of the basis. So we've got a symplectic form, a symplectic structure on this even dimensional space. And they then proved the following nice statement, that the delta constant stratum is Lagrangian. So remember, the delta constant stratum has got half the dimension of this C sub mu, because mu is even. And I just remind you of some definitions here, that if we've got a symplectic vector space W, then a subspace is isotropic. This is a term we'll need in a minute. If V is contained in its orthogonal complement. So this orthogonal complement is not really orthogonal. What it means is the set of vectors which, when paired with any of the vectors in V using the symplectic form, gives 0. So that what V perp means the symplectic orthogonal complement. to V. So it's isotropic if V is contained in V per, is co-isotropic if the opposite inclusion holds, and each of these inclusions has an implication about the dimension. And then it's Lagrangian if it's both isotropic and co-isotropic. And we say that a submanifold M of a symplectic manifold is isotropic or co-isotropic or Lagrangian if this is the case for each of its tangent spaces as a subspace of the tangent space to the manifold M. Okay, so in fact, the argument of Gieventhal and Barchenko also shows that for every K, the delta equals K stratum is co-isotropic with respect to the intersection form, to the symplectic form pulled back from the intersection form. The argument is not very difficult, involves 4 steps, which I'll sketch. First of all, the dimension of the delta constant, the codimension of the delta constant stratum is K, and so the omega orthogonal complement has also got dimension K. That's just a consequence of the fact that the symplectic form is a non-degenerate 2 form. So it's a non-degenerate pair. The key topological ingredient is that the intersection form on the cohomology passes to the quotient and defines the intersection pairing on the cohomology of the normalization. So remember, there's a map from the cohomology of Cu to the cohomology of the normalization. It doesn't go in the opposite direction. So H1 of Cu bar is the quotient of H1 of Cu by the kernel of the n upper star, where it's normalization. So it's not obvious that this should be the case, but it's a fact. And on the cohomology of the normalization, the intersection form is non-degenerate, because since C is irreducible, then the normalization of any singular fiber still has only one boundary component. And so we get the dimension of the kernel, the null space of the intersection pairing on this homology, on this cohomology, is just the difference in dimension of the cohomology of normalization and the cohomology of the curve itself, which is just the delta invariant. And then the next step is to notice that if I restrict the period mapping to the delta constant, to the delta K stratum, and then pull back the pairing, that's the same as the restriction to dk of this form that Gieventhal and Barthenko showed existed. This was their extension from the regular part, from the complement of D to the whole of the base space. So these two coincide. This was proved by Barchenko. And then kernel, so from this the kernel of the form on restricted to the tangent space of the fiber is the same as the kernel of P omega upper star. And over a smooth point of the base, then this is the final ingredient, the Gauss-Mannian, the covariant derivative maps the tangent space to the stratum isomorphically to the cohomology of the curve. And so the right-hand side here has 2h and k, and so we just have this sequence which shows that the complement, the orthogonal complement of dk is contained in, of the tangent space is contained in the tangent space. So that proves co-isotropicity. So let me just give you an example, just to make things a bit more solid. We take the versal deformation of A6 on 6 parameters, which are called A down to F. We take omega x, y, dx, and then Paul Cadman computed the pullback of the intersection form on the cohomology. This is the symplectic form on the base space. So I've written it as a skew-symmetric matrix, which simply lists in the natural way the coefficients of each of the generators of omega 2. So dA wedge dB has coefficient minus 3a squared minus c. So you get this nice and quite simple symplectic form. This is an invertible matrix because the form is non-degenerate. Finding the form, this is what work with Paul Cadman, was quite difficult and involved parametrizing the curve, the fiber in a neighborhood of infinity, and then a lot of calculation of residues. And the important thing I want to stress is that there is not a closed formula. There's not a simple formula that says the intersection form for A2K is the following. One has a method for calculating it. And this is one of the big gaps and one of the questions that I want to ask about. Anyway, I've got another example, which I like because it somehow looks like it looks rather like the generic version of the delta constant stratum. It looks as though it's a local calculation. It is not quite, but one can pretend that it is, and one can still learn something, and one can do some very easy calculations. So at the generic point on the delta constant stratum, then the discriminant is just a normal crossing of mu over 2 smooth sheets, and dk, where the delta invariant, well, is equal to k, is the union of all the k-tuple intersections of the sheets. If you're in k sheets, then delta is k. So in coordinates, which I'm calling q1 to q delta and p1 to p delta, d is just given by the product of the q's equal to 0. dk is the variety of zeros of the k delta minus k plus 1 tuple products. We can take the vector fields on, we have a very simple expression for the vector fields tangent to the discriminant. So this matrix chi is meant to shows the components of the vector fields tangent to the discriminant. So the first vector field in this is represented by the first column, which is q1 in the first place and then 0. It just means q1 d by dq1. That's our first vector field. The remaining vector fields are down to q delta d by dq delta. And then since the discriminant is a product in the direction of the p variables, they don't figure in its equation. The remaining vector fields are vector fields with constant coefficient 1, the remaining generators for the module of logarithmic vector fields. Now, I've kind of concocted this. This is a perfectly correct description of the discriminant and the dk. What we don't have here is a symplectic form, because this hasn't been constructed using the pullback. So we postulate, we imagine a symplectic form, and in fact the one we postulate is the standard form. And in this setup, I call this a toy example because everything works very, very easily. It's not, as I repeat, it's not really the pullback, it's not really the symplectic form that you get by pulling back the intersection form, but it looks like it, and it still tells us something. So I'll come back to this example a little bit later on. Anyhow, so we've introduced these strata. I've told you that the delta constant stratum is Lagrangian, and the other strata, dk, are co-isotropic. But we still haven't got any closer to finding equations for them. So that's what I want to do now. So we take the module of logarithmic derivations, der minus log d. So d is very well known to be a free divisor. That means that this module, der minus log d, is a locally free module. It was proved that it's a free divisor. This is where the notion of free divisor originated. This was work of Kyoji Saito at the start of the 80s. And we choose a basis for der minus log d, which naturally enough has mu generators. That's always the case when you have a free divisor in C mu, then der minus log d, which is a free module which coincides with theta of C mu with all vector fields outside the discriminant of all vector fields. So this chi matrix is going to play a crucial role in what we do. Now, omega is the matrix of coefficients of the symplectic form. Actually, I think I had actually called this form capital omega, but I'm just reminding you now that this is the form we obtained by pulling back the intersection form over C mu minus D and then extending it. This is a symplectic form on the whole of the base space, and I'm slightly changing my notation. Omega now is the skew-symmetric matrix of coefficients of this form with respect to the basis dui wedge duj. And we consider this following skew-symmetric matrix. We multiply front and back by the matrix chi. We transpose it on the left, and it's clear that the ijth entry is simply the value of this 2 form on the pair of vectors chi sub I, chi sub j. So if you write this matrix as kind of scoreboard, it records what the 2 form omega does to all the pairs of vectors, of generating vector fields. So initially this appeared to be rather just a way of recording some information. What is clear is that the ijth entry must vanish at points of the delta constant strata, because d delta is Lagrangian, and the vector fields in der minus log d are all tangent to d delta. So der minus log d is the vector field tangent to the discriminant, and in fact that therefore means that they're tangent to all of its naturally defined geometric strata, and in particular they're tangent to the delta constant strata. So if you have a point of d delta, then the value of the vector fields chi sub I and chi sub j at that point is each a tangent vector to d delta, and therefore omega evaluated on this pair is 0. So it follows that all the entries in this matrix vanish at points of the delta constant strata. And this was the original idea of our construction, that simply we get equations for the delta constant stratum, and we hope to get them by this means, simply by taking all the coefficients from this matrix. And that's actually correct. But slightly surprisingly, rather more is true. In fact, if we take the Pfaffians of this skew-symmetric matrix, then we can form the ideal of Pfaffians of different sizes. So the Pfaffian of a skew-symmetric matrix, so that this is something, I don't know, people that not everybody learns, so I'll explain it to you at the risk of offending those who do know. If you've got a skew-symmetric matrix of odd size, then it's easy to prove that its determinant is 0. On the other hand, if you have a skew-symmetric matrix of even size, then its determinant is a square, as it turns out, and there's a canonical formula for its square root, and that's called the Pfaffian. So the Pfaffian of a generic skew-symmetric matrix of size 2k is a polynomial of degree k. The determinant is a polynomial of degree 2k, the Pfaffian is a polynomial of degree k. So, we can form the ideal of Pfaffians of different sizes of this skew-symmetric matrix. And for each even integer, mu minus 2k plus 2, we form this ideal. And then the statement is that for each k, the stratum dk is the set of zeros of this ideal. So in particular, as I already said, the delta constant stratum is, well, I said the delta constant stratum was the ideal of entries in this matrix, but actually the entries are the same things as the 2 by 2 Pfaffians. I guess maybe I should point out that Whereas the Pfaffian means that you're doing something to a skew-symmetric matrix. The only skew-symmetric matrices that one has, or the skew-symmetric submatrices one has, are the symmetrically placed ones. And that's what is meant by the idea of Pfaffians. These are the symmetrically placed submatrices, of which one then takes the Pfaffian. So if you have a 2 by 2 symmetrically placed submatrix, then its diagonal entries must be 0, because it's a skew matrix, and its other two off-diagonal entries are the same, so its Pfaffian is actually just equal to the off-diagonal entry. So the variety of 2 by 2 Pfaffians is the same as the ideal of 2 by 2 Pfaffians is the same as the ideal of all the entries, so d delta is defined indeed by the 2 by 2 Pfaffians. That's an example, a special case of this, and the discriminant, which is d of 1, is defined by the unique mu times mu Pfaffian, that is the Pfaffian of the whole matrix, the whole skew matrix. So this is not very difficult to prove. The rank of the intersection pairing on H1 of Cu is just u minus 2 delta of Cu, because that's the rank of the homology of the normalization. And then, because the covariant derivative maps der minus log d, maps the tangent space isomorphically to the cohomology of a distinct fiber, it follows that the rank of the intersection pairing is the same as the rank of the skew matrix, which is the size of the smallest non-vanishing Pfaffian. So that's all one needs to prove this statement. So we get for free a set of equations of all of these strata. Well, I want to look at to reinterpret this slightly. So we take. How am I doing for time? What time did we start? Let's see. Okay, so we take the basis for omega 1 log d dual to the basis chi sub 1 chi sub mu. That means omega I of chi j is delta ij. So omega 1 log d is the dual of der minus log d, the hom der minus log d into the ring of functions on the base. So in fact, omega, this chi t omega chi matrix is the matrix of coefficients of the symplectic form in the basis omega I wedge omega j of omega 2 log d. And in fact, the ideal of Pfaffians of size 2k by 2k are just the coefficients of the kth wedge of omega of the symplectic form in the natural basis of omega 2k log d. So our ideal of the defining ideal for dk is the ideal of coefficients of a 2k form with respect to the generators of omega 2k log d. And well, since I'm a little bit late, I'll press on here. You can check when k is equal to delta is equal to mu over 2, when we have just one Pfaffian, then this all works very nicely. But I won't go into that. And one can calculate very easily for A6, for example, the matrix I showed you before, you can compute the delta constant stratum is defined by this idea, and you can compute with the toy example and get a rather simple form that shows that the 2 form that we guessed, the standard Mond 2 form, seems to be the right one. We get the right ideal of Pfaffians. Remember, the ideal of Pfaffians depends, of course, on the choice of 2 form. Okay. Now, associated with every symplectic form is a Poisson structure. That means it's a non-commutative ring structure on the ring of functions. So this is defined as follows. Omega defines an isomorphism from T star U, C mu, to T C mu, and so it converts a one form into a vector field, which I call omega flat. So if you've got a one form omega, you can convert it into a vector field omega flat. And then you define the Poisson bracket of two functions, A and B, to be the evaluation of omega on these two vector fields. Actually, there's a much simpler formula for the Poisson bracket, because in order to convert the one form dA into a vector field, you have to multiply it by the inverse matrix of omega, similarly for dB. And so when you pair them, in fact, you're simply multiplying together omega by omega inverse twice, and the formula simplifies to this in this way, that you write down the exterior derivative of the function A as a row vector, and on the right-hand side of omega in minus 1, you write down the exterior derivative of B as a column vector. So, if you have a coisotropic submanifold of a symplectic manifold, then coisotropicity is equivalent. Oh, sorry, this says I of V. This should say I of M, where ideal functions vanishing on the submanifold is Poisson closed. So V here means M. So that's a very well-known statement I won't go into. We conjecture that all of these ideals, the ideals of Pfaffians, are first Poisson closed and second reduced. And we have no proof of either of these statements. We've checked them. It's obvious that if they're reduced, if the ideals are reduced, then these are the ideals of coisotropic submanifolds, singularities, but nevertheless coisotropic if they're smooth points, from which Poisson closedness follows. But we don't know that they're reduced a priori. So this is a conjecture, but it's checked for quite a range of singularities. It's not too hard to compute, and we see that these are true. But the problem is how to prove this. So I said that we have no real algebraic handle on the two form, on the symplectic form. It's calculated by a kind of ad hoc method. We don't have a closed formula for it. It's very hard to combine it and make the calculation which would show Poisson closes. That's quite a delicate calculation. So, just a couple of applications. Using this way of getting equations for the delta constant stratum, Paul Kaplan was able to show that for E6 and D8, the delta constant stratum is indeed Cohen-Macaulay as conjectured. For A4 and A6, all of the decay, all of these Severi Strata are Cohen-Macaulay. We haven't checked for D8, but for E6, D2 is not Cohen-Macaulay, so they're not all sadly Cohen-Macaulay. So I'm a bit worried about time. I want to go on briefly. Well, actually, would like to go on at great length, but obviously I can't. So the crucial point here is to point out that the matrix of coefficients of the basis for der minus log d can always be chosen symmetric. And this turns out to be rather important. I'm not going to dwell on the proof. It's explained here, but essentially it's used, what it uses is Gorenstein duality. The ring O sigma F is free over the ring of functions on base space, where sigma F is the relative singular points. And because this is a Gorenstein ring, there's a perfect pairing. It's also known as the residue pair. Anyway, one can construct by this means a basis dual to this basis, and it then turns out that if you the matrix of vector fields is actually the matrix of multiplication by F with respect to this dual pair of bases. Dual basis in the source here, we identify this with mu, the direct sum of mu copies of O C mu by means of this choice of basis, and this also by means of this basis. And now, because this is, it turns out that this is self-adjoint in an obvious way with respect to the Gorenstein pairing. From that, it follows that the matrix chi is symmetric. So we've got a symmetric basis, which in particular allows us to write chi omega chi in place of chi t omega chi, and allows us to do quite a lot more. I'll just mention two things in this connection. The first is that we can put these two perfect pairings, the obvious perfect pairing between omega 1 log d and der minus log d, which is just the standard pairing of one forms with vector fields, and the Gorenstein pairing. And this gives us a natural isomorphism from omega 1 log d and the vector fields, the one form, logarithmic one forms on the base space, to vector fields on the base space. By using both perfect pairings. So that neither pairing gives you a natural map, but combining the two pairings gives you this isomorphism, which I won't spend long looking at. But the important thing is that it sends omega I, the ith generator of omega 1 log d, in the basis dual to der minus, to the basis we've chosen of der minus log d, to d by ui. And for this reason, it makes sense to think of the columns of the chi omega chi matrix into vector fields. The jth column is actually the vector of coefficients of this one form in this basis, and the duality isomorphism turns it into this vector field. And the remarkable thing, which is again experimental, is that these vectors form a Lie algebra. That is, if I take the Lie bracket of any two of these vector fields, then it's a linear combination with coefficients in OC mu of these vector fields. So this seems to be rather a delicate property. It's checked for quite a lot of examples. And it's worth noticing that if we replace the symmetric basis chi by a non-symmetric basis, which means, of course, we have to revert to the form chi prime omega chi, sorry, chi prime transpose omega chi prime, then the Lie algebra property fails. And if we replace the two form omega by a different symplectic form, then again, the Lie algebra property fails. So, I said that I have more questions than answers here. We so far listed various things we can't prove, although we can calculate. That these ideals of Pfaffians give us the reduced structure for decay, that they are indeed coisotropic, and that this mysterious Lie algebra really is a Lie algebra. So let's skip. And on to the very last point, that I want to emphasize this chi omega chi matrix. That seems to be the central character in this story. In fact, it has a further role to play. Remember that this is a Cohen-Macaulay module of rank 1 over, sorry, this should say, oh yeah, this is correct. This is a sigma 0f, that's the set of critical points with critical value 0 in the total space. That's a Cohen-Macaulay module of rank 1 on OD. So one can, the Cohen-Macaulay module is the same as the dimension of OD over OD. It's also a maximum Cohen-Macaulay module of rank 2, and it fits into a short exact sequence. O sigma 0f, I'll explain how that's constructed. In fact, there's a Let's see if I can make this work. So here's a little quick diagram that shows you how to construct the mappings and allows you easily to prove that the sequence is exact. So this tells us that this short exact sequence is an extension of O sigma 0 by itself, and therefore determines an infinitesimal deformation of O sigma 0f as OC mu mod. So O sigma 0f as a ring is rigid because it's smooth, but its structure as an OC mu module or as an OD module is not rigid, and this gives us a canonically defined infinitesimal deformation. So one can prove that it doesn't depend on the choice of coordinates on the base space, nor on the choice of symmetric basis for the module of logarithmic derivations. And I just want to emphasize that it's somehow the crucial object. Associated with this object, m sub omega, we have its skew-symmetric presentation matrix and the Pfaffians of this skew-symmetric presentation matrix, which are the natural things to consider in the presence of skew-symmetry in place of fitting ideals, define all these interesting strata and have this nice co-isotopicity property, which, as I say, we don't really understand. I ask, is there a structure theory for such objects? So we have a skew-symmetric matrix determining an extension. Can we prove that the codimension of the strata is always what we find it to be in this example, in this range of examples? Can we prove some general Cohen-Macaulay property using a generic structure? Well, I don't know the answer to any of this, so that's why I'm giving the talk. Anyhow, to reiterate, I'm just finishing. The key object for these irreducible planes of singularities, which encodes all of the interesting behavior, is this skew matrix, chi, omega, chi. So on the other hand, for singularities in general, the organizing center is quite different. Pepe. So, happy birthday and long and
Okay, so is there any question?
Is this all for irreducible curves?
Yeah.
And anything known about reducible ones?
We haven't tried, but I guess one could do something, but there's no longer a symplectic structure, because the intersection form on the cohomology is degenerate. So when you can pull it back, it's a two form, but it'll be closed, but it won't be non-degenerative. So I guess using that you can do something, but I don't quite know how to do it.
Okay, any other question?
Any idea what happens in modular meter?
I don't think it complicates the situation. I think my argument skipped over it, but I think that the key point is that the Gauss-Length derivative, the covariant derivative, should give an isomorphism from the tangent space to the stratum to the cohomology. And that seems to work for the smallest strata, the right equivalent strata. So I think it's okay, even with one.
More question? If not, let's thank the speaker.